Thanks for downloading the InOurTime podcast. For more details about InOurTime and for our terms of use, please go to bbc.co.uk/Radio 4. I hope you enjoy the programme. Hello. Black holes have been described as the dead, collapsed ghosts of massive stars. They have an irresistible gravitational pull. Even light submits. Their dark, swirling, ever-hungry mass has fascinated thinkers as diverse as Edgar Allan Poe, Stephen Hawking, and countless science fiction writers. When their ominous existence was first predicted by the Reverend John Mitchell in a paper to the Royal Society in 1783, nobody knew what to make of the idea. They couldn't be seen by any telescope. Although they were also suggested by the 18th century Marquis de Laplace, and their existence was proved on paper by the equations Einstein's general theory of relativity, it was not until 1970 that Cygnus X1, the first black hole, was put on the astral map. What causes black holes? Do they play a role in the formation of galaxies? Will they eventually swallow everything up? And what have we learned of their nature since we found out where they are? With me on this voyage into the black hole is the Astronomer Royal, Sir Martin Rees, author of many books, including Before the Beginning, Our Universe and others. He's Professor of Physics and Astronomy at Cambridge University. Jocelyn Bell-Burnell, Professor of Physics at the Open University, and Professor Martin Ward, Director of the X-ray Astronomy Group at the University of Leicester. Martin Rees, you described them to us as collapsed stars, as black holes. Can you give a description of how a star collapses and how it becomes a black hole?
A star is held together by gravity, and the smaller a star gets, or the heavier the star is, the stronger gravity is. We know that in the case of the Earth, gravity is what holds us down. That's why Gagarin had to have a fast rocket to escape from Earth's gravity, and to escape from the surface of a normal star, you would have to fire a rocket at about 1,000 kilometers per second. But if you imagine something which is much smaller than a star or much heavier than a star, the speed you need to escape from it becomes much larger, and eventually it may become so large that not even light can escape. And a black hole is an object where gravity has overwhelmed all other forces, and it's contracted so much that not even light can escape from it. So a black hole is an object in space that exerts a gravitational imprint on its surroundings, but which puts out no light. Everything has collapsed, light can fall in, objects can fall in, but nothing can get out because space is so warped, as it were, that not even light can escape.
Right, now that's very clear, but there's a lot of ideas inside that, so I just want to go back over it quietly. This star collapses. Gravity, that is the pull of the star towards the centre of itself, towards a singularity, becomes fiercer and fiercer and heavier. Therefore, to get away from it, it becomes harder, and even light travelling at 160,000 miles a second at once is not fast enough to get away from this. Now, what causes the collapse of the star in the first place? And can you just explain a little about what you call escape velocity, about getting out? Like Gagarin got out, but we fired a rocket. It's quite easy to get out of the Earth. It's harder to get out of the Sun, as I understand it. Right. It's impossible to get out of a black hole. Now, can you just go into that a little bit more?
Yes, well, if the Sun were smaller, it would be harder to escape. And indeed, we do have objects which are not quite black holes, but where gravity is very strong. In fact, these are objects called neutron stars, which Jocelyn Bell-Burnell here was co-discoverer of. A neutron star is an object which is as heavy as the Sun, in other words, 1,000,000 times as heavy as the Earth, but is no bigger than the size of London. And on an object like that, gravity is clearly immensely strong, so strong that you have to fire your rocket at half the speed of light to escape. If you're on a neutron star and you dropped your pen on the floor, it would not just make a noise, it would produce as much energy as a kiloton of high explosive. So that's a measure of how strong gravity is when you have a very large mass in a small space. Now, if you take a neutron star and imagine compressing it a factor of 3 smaller still, down to a size of, say, 3 miles across rather than 10, not even light could get out. And then it would be a completely dark object seen from outside, and it would become a black hole where something happens inside it that we can never understand, but to the outside world it's just something which exerts a gravitational pull and nothing else.
Jocelyn Bell-Burnell, when the Reverend John Mitchell announced in 1783 a definition of a black hole, which is a brilliant 3-line definition. Yeah. It reads very clearly now. But what interests me is how he got there without Einstein, without telescopes, without technology. Can you tell me how he arrived at that conclusion, which is only over the last 30 or 40 years been explored in any sort of certainty by people like yourselves?
He was working with a picture of light that was invented by Sir Isaac Newton. It's called the corpuscular theory of light, which is still a picture that we use in many, many ways in contemporary science. And what Newton envisaged was that light was a stream of little bullet-like things, little particles, and that each of these corpuscles actually had weight. And gravity would pull on that weight, just like if you try and lift a bottle of water. Light would have a weight like the bottle of water, and gravity would be pulling it back. And what Mitchell was doing was saying, how much gravity does there have to be to pull the light back and stop it escaping? And that at heart is what he was doing.
So it was a thought experiment, as simple as that.
Yes, yes. And
I'm
guess,
still intrigued that working from Newton, he got, as it were, beyond Einstein.
Quite often find in science that there are parallel ways of looking at things, and as scientists we often use a lot of different pictures to help us understand. All the time you've got to remember that it is a picture, it may not be the actual thing, and that there are times when these pictures or analogies will let you down. So he was using a picture that one could still use today, but we don't happen to use very often.
Was that ever taken up? Do we know of the existence of his theory now because of what we know now, rather than people taking it up and saying, Mitchell said that in 1783, I can build on that and develop from that?
I think, my guess is that we know of it because of hindsight. I think at the time it probably didn't make a great impact. People will have said, oh, that's an interesting calculation, pity it ain't relevant to the real world, and passed on. And it was only much, much later that the topic was revisited, and I guess that Mitchell's quote and Laplace's quote were subsequently dug out again, and people said, oh, look, they thought of this way back in 1784 or whatever.
Martin Ward, is it unusual in science that something is discovered theoretically first and then found much later, as it seems to be the case with the black holes?
Not particularly. There are examples in particle physics where one has a certain model, and based on that model, particles that have not been yet observed are predicted. And then
Can you give us some examples?
Well, the Higgs boson, I'm not a particle physicist, but there are many examples of this. And then particle physicists build huge accelerators to test these particular models. So there are a number of examples. And of course, a good theory will make predictions that one has to go and test. A theory that makes no predictions is not a very good theory.
And so, when did, as it were, the practicalities catch up with the theory in the study of black holes?
How do we actually observe black holes? I mean, I'm an observational astronomer. Martin is a theoretical astronomer, so he interprets our observations. And of course, observations is what we have to move forward. It turns out that black holes can be detected, observed, inferred by various types of observations, and I won't give you a complete list because it's very long. But the interesting thing is what happens to matter. What do I mean by matter? I generally mean gas that comes from somewhere else outside of the black hole, is pulled in by gravity, as Martin explains, towards the black hole, just in the same way that the planets are orbiting around the sun. This gas is orbiting around the black hole, and gradually it's pulled in, it spirals in. And one of the ways we can actually observe them, we can infer them, is because this gas gets extremely hot. It becomes very dense because it's compressed, and it emits X-rays. And my particular discipline of X-ray astronomy is, of course, important in the detection of black holes because that's what we use to actually see them. The hotter things get, the higher energies they emit. It's the analogy with the furnace. If you have an ordinary furnace, it glows red. If you wind up the temperature, it gets to be yellow and then blue and then goes into the ultraviolet. The stuff that falls onto black holes gets even hotter, millions of degrees, and then we see it in X-rays. That has to be done from above the Earth's atmosphere.
So that actually took a development in technology to get there, because Martin Rees earlier referred to the gravitational imprint. So if we're going to be strict about the word black, we cannot see them, and so we're inferring them from adjacent
processes that occur near to the so-called event horizon. There are other ways to infer their existence, and that is by their effect on other bodies, not by making them very hot, but just by disturbing the motions of stars, for example, near to a black hole, such as we may have in the centre of our own galaxy.
Martin Rees, what does a black hole do to space-time in Einstein's general theory of relativity?
Well, the reason black holes are fascinating is they exemplify the way in which Einstein's theory leads to surprising and counterintuitive conclusions in extreme situations. When gravity is very strong, or when motions are very fast, so things are moving at about the speed of light, then we are not surprised that we have to go beyond Newton's theory. This is why we can understand black holes better now than Mitchell was able to 200 years ago. We have a theory that can cope consistently with these extreme situations. And according to Einstein's theory, a black hole is an object where there's a definite sort of surface, which is the place from within which no light can get out. And outside this surface, we can calculate how gas or stars would move, and that, as Martin Ward explains, is how we can infer the presence and properties of black holes. But what fascinates scientists and physicists in particular about black holes is that deep inside them, in the region that we can't directly observe, there lurks a very basic mystery indeed.
The singularity.
The singularity is so-called. And the idea here is that deep inside the black hole, gravity becomes stronger and stronger and stronger, and eventually, according to the theory, it becomes infinite. Black holes point towards places we can actually observe in our universe where physics transcends what we now understand.
And also black holes bring in this remarkable business of light bending, which Eddington in 1919 sort of proved empirically with the eclipse of the sun to justify, to validate Einstein's theory. But can you just talk about light bending, Jocelyn Bell Burnell, and in terms of the event horizon around a black hole? I'm using a term that I've got from you three, called the event horizon. And sometimes if light goes towards the black hole, it disappears into the black hole. I mean, we're talking fantasy as far as I'm concerned, but here we go. And and other times it bends around it. Now, can you tell us why sometimes light just disappears into this hole and is no more, and cannot get out? I think we must keep emphasizing that, because once you're in this black hole, not even light can get out, and light travels faster than anything we know, and that can't get out, so nothing can get out. So light disappears to this singularity that Martin says is beyond physics at the moment. But some light, seeing the black hole through the event on the horizon, as it were, the event horizon, bends.
Yeah.
Now it's over to you.
Right. I have a picture of a tabletop, not a very smooth tabletop. It's a billiard table, but it's got dents in it. And as you shoot a ball across this table, it gets deflected by the dents. A black hole is not just a dent, it's like a plug hole in your billiard table. I mean, it goes right through to the darkness underneath. Instead of a billiard ball, we now have a ray of light, but it behaves the same way. And where the space is flat, it trundles straight. But where there's a dimple in space, it curves, just like your billiard ball curves. And where there's a black hole and it heads straight forward, it goes whoops and down the hole. Now, if you keep a bit away from the plug hole, where space is still a bit curved, but before it's gone really pluggish, hole-ish, then you can also get the light bent, but not falling in. If you aim light straight at a black hole, it's going to go down the tube. But if you aim light a bit past the black hole, it'll just get bent. And what Eddington was doing in that eclipse expedition just after the First World War was checking out a prediction of Einstein's that mass and gravity would bend light. He wasn't using a black hole, he was actually using the sun. He was using the sun at the time of an eclipse so that the sunlight was blocked out. And you could actually see what was happening to the rays of light from beyond the sun as they came past the sun. And so what Einstein was checking out was how much bend is there in a light ray as it goes round the edge of one of these dimples in our billiard table.
And can we just, before we leave the anatomy of the black hole, Martin Ward, can you tell us about the event horizon? Can you describe what that is and why it is so important?
It's essentially an interface between the what goes on inside the black hole and what goes on in the rest of the universe. And the importance of the event horizon is that after something has passed through it, whatever that is, light or gas or anything, after that, its properties become very simple. It adds to the mass of the black hole, and therefore the event horizon gets a little bit bigger, but then it can't communicate by any means. Radio waves, any sort of communication is impossible after the event horizon. So we have to rely on the theory to know what happens to matter after it's gone through. So there's no more communication with the outside universe.
As I understand it, your team at Leicester was the first in the world to discover physical evidence of medium-sized black holes. Is it possible for you to sum up the significance of that?
We looked at a nearby galaxy. Everything's relative terms, isn't it? It's about 9 million light years away. This is in our backyard by our standards. And we looked at it with an X-ray telescope, and I won't go into technical details, but it has tremendously fine resolution, acuity of vision, which we didn't have before for X-ray telescopes. The universe emits radiation across the electromagnetic spectrum. X-rays is one part. Before we had a blurred view, and now we have a clear view. We looked at this particular galaxy and we saw a bright X-ray source, which was so bright that if we use the standard arguments that astronomers use to infer the mass of a black hole, one of them, then we believe that it has about 500 times the mass of the Sun. So this is in between the...
Not the size, but the mass of the Sun.
The mass of the Sun,
yeah.
Yes. So this is in between the small ones, diddly ones of a few times the mass of the Sun, and the huge ones in the centres of quasars, which are perhaps 1 billion times. Now, what's the significance is that this particular source was not in the centre of the galaxy. And we would normally think that these massive black holes, because of gravity, as Martin explained in the beginning, would form at the very centre, because that's where the mass is. But this is many hundreds of light years away from the centre. So the question is, first of all, is it an intermediate mass black hole, and other interpretations possible? If it is, how on earth do you form these things not in the centre of the galaxy? It could be cannibalism, actually. It could have been a passing galaxy which had a black hole in its centre, which had an accident, crashed into the other galaxy, and so we're just as a snapshot seeing this little black hole by chance away from the nucleus.
You're just making it up. It's fun, isn't it?
That's one theory. But what's the significance? I think if it is an intermediate black hole, then how do you form these things? If we could understand that, and it's a nearby example, so we can study it in detail, maybe we've got clues to how to form the really massive ones.
Jocelyn, you found these small black holes. What is the difference? Are there any distinction between the small black holes and those of intermediate size and supermassive size? And
can we just clear up what we mean by size? Because I think we're probably confusing the audience a bit. When we, as professional astronomers, talk about the size of the black hole, what we're usually talking about is the size of the event horizon, that mythical surface round the black hole, which is its Rubicon. And if you cross that event horizon, you are going down the black hole, come hell or high water. The physics of the star size, the intermediate mass, the supermassive black holes is all very similar. They are large gravitational masses with this so-called singularity at the centre, and round them this event horizon. But interestingly, the effects that you would feel as you fell into these different kinds of black holes are different. The star-sized black hole, as you cross the horizon there, you would feel the effects not just of gravity, but of the gradient of gravity tearing your body apart. Whereas if you were going into a supermassive black hole at the centre of a galaxy, you actually don't feel that effect until much, much, much later, which in that case is too late.
Can I come back to you for a moment, Martin Rees, and then go? And what role do you see it having? Are the words? That's why I'm stumbling around for words. Are the words like role and function? Are they relevant at all in this?
They do indeed play two important roles. One is that they are the end point of stars, and so if we came back and looked at the universe in the far future, a lot more of the stuff would have ended up in black holes and these dead remnants, because gravity eventually will have won and swallowed up a lot of material. So there's a general trend towards more and more of the material ending up in black holes. But they're also important to astronomers in trying to understand the universe, because they are able to manifest their presence in a very conspicuous way. Although a black hole doesn't put out any energy, something falling into a black hole releases a tremendous amount of energy. I mentioned that if something falls onto a neutron star, it releases a lot of energy in an explosion. And if something falls into a black hole, it releases far more energy per kilogram that falls in than you can get in any kind of explosion, even a nuclear explosion. And what this means is that black holes, when they are not in empty space but are surrounded by stars and gas that they are able to capture in there more, they shine very brightly. And indeed, some of the most spectacular objects in the universe that we observe, things called quasars, objects sending out jets, and exploding stars of various kinds, are energized by black holes which are interacting with stuff close to them.
Martin Rees referred to the sorry about this cold, Big Bang 10,000 million years ago, or slightly more. And it has been suggested by Hawking that maybe black holes were there at the start of that, and that they could be something to do with creating and seeding the galaxies. I think seeding is your word. Can you just discuss that possibility?
I think it's a sort of chicken and egg argument, and that is fundamental question is what's the dominant energy output process of the universe? One of the fundamental questions. And there are sort of two contenders, really. One is star formation, in the same way that the Orion Nebula, for example, is an example of stars forming in our own galaxy. It's called a stellar nursery sometimes. And these processes, of course, are nuclear processes, as Martin Rees has said. They're not terribly efficient, in fact, in converting matter into energy by the E equals mc squared. Black holes are more efficient, 10 times or even more than 10 times more efficient. And we don't actually know at the moment, in the early stages of the universe, what the dominant energy process was, whether it was accretion, that's a technical word, that means material falling onto the black hole, accreting onto the surface, not the surface, through the event horizon, I should say, and that produces a lot of energy, or is it star formation? And it's a big open question, and the early generation of black holes, say ones that were formed perhaps just 1 billion years after the Big Bang, these are hypothetical, but they could have provided the seeds for galaxy formation, this work that Martin Rees has done.
Are black holes always, as it were, on the retreat? Because if they're always on the retreat, then the idea of them being a seeding wouldn't seem to me to make any sense. But what I've heard so far is that they get smaller and smaller and have and more mass, pull more and more in, eventually reach a singularity, which you've got zero... it's got infinite density and zero size. That's right, zero size. And so are all black holes destined to disappear in that way? And if so, how can they be part of an expanding universe, as it were?
No, I think there's a misconception here. I mean, they don't...
Well, if you could clear it up, I'd be very obliged.
They can't get smaller. The event horizon can only be what it is now or larger if it accretes more material. As it accretes more material, the event horizon will scale up and become large. So in the sense of them disappearing, perhaps the misconception is to do with whether we see evidence for them. It's believed that these very energetic things called quasars that were formed in the early universe and emit tremendous amounts of energy, as much energy as the entire star output of energy from our galaxy in a region the size of the solar system. But of course that only works if they're feeding, another rather colloquial term, if material is falling onto them. If that dries up, if they stop feeding, then the black hole becomes really black, because it's only the effects of the matter falling onto through the event horizon that produces the energy. So it may be that there are black holes sitting there which are not feeding, which we can't observe. So the era of black holes producing huge amounts of energy may be over, but they're still there. They haven't disappeared.
Martin Rees, this would lead me on to the conclusion that if black holes are sucking everything in that comes anywhere near them, that eventually everything will be sucked into one black hole or other. That we're all destined, the future of the universe is that we all end up in a black hole.
Yes, things aren't quite as apocalyptic as that. Black holes...
I'm just trying to encourage you.
Sure. Black holes are indeed growing. But we are, for instance, at an extremely safe distance from the one in the centre of our galaxy. There's no danger of that swallowing us up. So, indeed, although they are growing, it would take a very long time before they swallowed up more than a tiny fraction of the galaxy. So,
but also not to be apocalyptic, but to look far forward. I mean, you people around this table speak very easily of sort of 10 billion years ago and that sort of thing. Let's just take the odd billion or so years ahead. I mean, our black holes, they're not going to go. Well, are they going to go away? Are they going to grow? What's going to happen there?
There are tiny effects which are beyond what Einstein predicted in his theory, which allow for the microstructure of space and the effects of quantum theory. And these will gradually erode away black holes. And this is an effect which wasn't in Einstein's theory, but has been included later, and this will cause a so-called erosion or evaporation of black holes, but the time we're talking about over which this operates is far, far longer than the age of our present universe. And this, I think, indicates two things about the importance of black holes. One is that although we understand black holes well enough to interpret some of the astronomical observations, there are still mysteries about the details, and also they do point towards new physics that may manifest itself deep inside black holes and will manifest itself in present-day black holes in the far future.
Briefly, Jocelyn Melbourne, is it possible to tell us what the effect on space and time is of the black holes? I mean, if this studio went into a black hole, what would be the effect on our space and time?
If this studio right now started falling into a star-sized black hole, a star-mass black hole, as opposed to one of the bigger ones, the first thing that would happen is we'd begin to feel our bodies being pulled apart. Because not only was the gravity strong, but there's a very strong gradient of gravity, which means the gravity on the lower part of your body is much bigger than the gravity on the upper part of your body. And it's sufficiently strong that it would ultimately rip things apart in a most unpleasant manner.
Spaghettification.
Spaghettification, yes. You get long and thin. You go in sort of stranded.
A lot of people would pay for that.
It's not a pleasant experience. If there was somebody else on another planet able to observe us and the studio falling into the black hole, if they could watch the studio clock, which I'm sure is very precise, they would find it was running slow. And the closer we got into the black hole, the closer we got to the event horizon, the slower the clock would go. One of the things that people in my speciality have to be aware of, where you're dealing with pulsars, which are very accurate clocks, we have to be aware that our watches, our clocks, run at different rates between new moon and full moon. It's only about a millionth of a second difference, but it is there. And it's because at new moon, sun and moon are on one side of the Earth. At full moon, sun and moon are on opposite sides of the Earth. And so Earth experiences slightly different gravity in the two circumstances, and our clocks go at slightly different rates.
But the main reason why we study black holes is twofold. I think first is they're clearly an important part of our cosmic habitat, which is really part of our environment. And secondly, gravity is a fundamental force of nature. And there's a limit to what we can do experimentally on Earth. And the cosmos provides us with a way in which we can study the laws of nature and the forces of nature under far more extreme conditions than we could ever simulate on Earth. And so if you want to understand forces such as electricity, nuclear forces and gravity, then we can learn a great deal from these observations. And black holes in particular are objects that extremely strongly manifest the effects of gravity. So that's the motivation, I would say.
Well, thank you very much, Jocelyn Bell-Burnell, Sir Martin Rees and Martin Ward. And next week I'll be discussing the Glorious Revolution. So there we are. Thank you very much for listening.
We hope you've enjoyed this Radio 4 podcast. You can find hundreds of other programmes about history, science and philosophy at bbc.co.uk/Radio 4.